Hello Internet, this is Oscar again, this time with a video on one of the more confusing topics in numerical analysis, which is convergence order. I'll define it and then go through some examples with you before showing you how this relates to speed. We'll also compare this to Big O. If you've seen other videos on this channel, you'll know that I bring up order a lot.
Now about the order of fixed point iteration.
Let's have a linear order. But bisection always has a fixed constant multiplier of a half. Newton's method we know has a quadratic convergence, but so does Stefanson's method. In that order of convergence, Wettstein writes that this is actually a quadratic convergence, but he doesn't actually prove it. Let's talk about the order of Muller's method. The order of Duran-Kerner is quadratic. It does require that you have d derivatives in order to be able to use it, but it does give you d plus 1 convergence order. And many other videos. Let's start with error, or in this case, the absolute error, meaning how far away our current guess is from our actual solution x star. Here's our equation for error, given that our next value for our error is some constant m times our previous error raised to an alpha. That alpha is our order. Generally, the higher the alpha, the fewer iterations you'll need. Let's take that error equation and step it back one iteration. Using these two equations, we can divide them and eliminate our m term. Then take the log of both sides. From here, we can use properties of logs to extract that exponent. Then solve for alpha, giving us this equation. Let's try to compute alpha for bisection using the function x squared minus x minus 1. We'll start from the interval 1.618, and run it for a few times. Afterwards, let's compute the error after every step. Then, using our alpha equation, use the first three errors to come up with our first alpha of about 1. Then, the second set of three errors to come up with the next alpha, which is also about 1. Then we'll fill in the table with the rest of our alphas. Once we have alpha, we can find m. Starting from our error equation, we simply solve for m. Then, using a pair of errors and its corresponding alpha, plug everything in to give us an m of about 0.5. Look at the next pair of errors along with its corresponding alpha. This also gives us an m of about 0.5. Indeed, bisection has an alpha of 1 and a value for m of 0.5. This makes sense because we're reducing the error by half every time. Let's try to compute the alpha for another refining method, in this case, false position. We use the same example from earlier of x squared minus x minus 1 equal to 0, but now we'll need a larger interval because this one converges much more quickly. From our interval, 0, 2, we perform a few iterations of false position method. Then we can compute our errors, and afterwards we compute our alpha. Notice again that alpha in this case is about 1, meaning this is converging linearly. Indeed, for false position method, it's a linearly convergent function, and in this example, our m is about 0.15. Note though that m is going to change depending on the function and root finding method. Let's do one last example of computing alpha, in this case, Newton's method. Using our same example function from earlier, let's start from the value of 2. This converges relatively quickly, as you can tell. Afterwards, we can compute our errors, and then compute our value for alpha, which is going from anywhere between about 1.9 to 2. And Newton's method is normally quadratically convergent, meaning alpha is 2. And in this example, m is about 0.4, but note that that's going to change depending on a few factors. Another factor that can impact your speed, other than alpha, is the amount of function calls your method has. For example, secant method has an alpha of about 1.618, compared to Stefanson's method, which has an alpha of about 2. Both of these methods need 2 function calls. The difference is that secant method only needs the 2 function calls at the beginning. Afterwards, we can save the value from the last iteration's function call. With Stefanson's method, we need 2 new calls each iteration, which can indeed take longer. If we apply both of these methods to the function x cubed minus x squared minus x minus 1, they both take 6 iterations to converge. The difference is that Stefanson's method takes longer. Let's evaluate the function of x to the 8th plus 15x to the 4th minus 16 using these root finding methods with increasing alphas. Here are the number of iterations it takes to find the root, starting with about 45 with bisection, and then slowly increasing in speed, lowering the number of iterations until about 2 where it plateaus. Let's then look at the runtimes for each of these methods, with bisection being by far our slowest, and then speeding up as we increased alpha until that plateau mark, where doing 2 iterations that are more complicated didn't save us on runtime. We also are not including the amount of time needed to find the derivatives, which, if they are not given to you, needs to be included as well. A quick note on Newton, Halley, and Householder. Each of them require multiple function calls to f, f prime, and so on. In the last example, I coded them symbolically to remove those function calls from the methods. For example, Newton's method looked like this, Halley looked like this, and so on. So the last example didn't include function calls. If we look at Newton, Halley, and Householder more generally, these are the number of additions and subtractions each iteration needs, as well as the number of multiplications and divisions, raising to powers, and function calls. This doesn't quite tell us the whole story, though. Let's multiply these against the typical number of iterations from our previous example. Here, you'll notice that they have essentially the same number of function calls. This, though, is still kind of misleading. Let's actually break it up. Now our table looks something like this. If our function was something like x cubed minus x squared minus x minus 1, then those higher order function calls get smaller and smaller. So you might prefer using something like a higher order function like Householder 3. If our function was something like sine of cosine of e to the x, then needing those higher derivatives starts to look much more complicated. And in this case, you might prefer something low order, even linear. But how fast is linear? If we take our error formula and use, for example, bisection, we know that alpha is 1 and m is a half. We plug those into our error formula, we now have this of our next error being our previous error halved. So, how long would it take us to find a b minus a in absolute value that's less than some tolerance epsilon? We'll just assume that b minus a is 2 and our ending tolerance is 10 to the minus 12. With b minus a equal to 2, that means the most our error could be is 1. Our next error would be 1 divided by 2, and then a half divided by 2, and so on. What we're really looking for in this case is 1 over 2 to the n, giving us our tolerance epsilon. Doing a bit of math, we can come up with this equation. Then if we take the logs of both sides, we can isolate n. Therefore, log base 2 of 1 over epsilon gives us our value for n. In this case, our method would take about 40 iterations. Using the same approach, let's figure out how fast quadratic actually is. Using our error formula, we'll use Newton's method as an example with an alpha of 2. We don't know what m is, but that's not going to matter a whole lot, and you'll see why. This gives us our new error formula, and then the question we need to answer is, how long would it take for our error to get smaller than some epsilon? We do need to assume that this is converging, otherwise this could take literally forever. And that our first error is going to be greater than 1. The ending epsilon we'll use is something like 10 to the minus 12. For the sake of argument, let's just say that our first error is 2. This means our next error would be m times 2 squared, or m times 4. We made the assumption that our method was converging though. This would mean that our next error should be smaller than our last one, which would make m less than a half in order for this to be true. Let's use m of a third, giving us our next error of 1.3 repeating. Let's then use that same a third times 4/3 squared to give us our next error of 16/27, and so on and so forth. After some time though, we'll need to change gears because our error squared is going to matter a lot more than our value for m. Here's what I mean. At some point, we'll get to an error of about 0.1, and for illustrative purposes, I'll just make m equal to the value of 1. Plug those into our error formula. We'll say 1 times 0.1 squared, giving us 0.01. Our next error would be 1 times 0.01 squared, giving us 0.0001. Plug that in, we get 10 to the minus 8th. Our next error would be 10 to the minus 16th, and giving us about 8 iterations total. When you're close, our error term is really what counts. Let's just say 0.1 squared raised to an n to give us our tolerance of 0.1 to the 12th. Essentially, what we're saying is 2 to the n equal to 12. Using logs, this says we need about 4 iterations once we're close. It could also be helpful to view order as the amount of accuracy in terms of digits you're gaining each iteration. For example, with bisection, all you're doing is reducing the error by half. You're gaining about 1 or fewer digits of accuracy each time you run. With Newton, you're doubling the amount of digits you're gaining. Halley, you're tripling. Householder 3, you're quadrupling, and so forth. With secant method, an order about 1.618, you're tripling about every other iteration. You might also expect that when you're close and using a root finding method with an order greater than 1, it should take log base alpha of d iterations to converge, where d is the number of digits of tolerance, which you can write as log of 1 over epsilon. Let's go back to this example from earlier, which indeed did take 4 iterations. But now let's start further away. Starting from about 10, it takes Newton's method a lot longer to converge on root. If we compute the errors after every iteration, we can then compute the orders alpha. Notice that Newton's method starts relatively linearly and then speeds up close to quadratic as we get closer to the root. We can also compute the m terms and note that these are not constant. What I really want you to know from this example is the importance of picking a good starting point for root finding methods. There's another method of comparing algorithms commonly used in computer science known as Big O. When we talk about order, this is a measure of how much we're reducing the error by every iteration. So for example, linear order is slower than 1.618, is slower than quadratic, and so forth. With Big O, it is a measure of algorithmic time complexity from some input size n. So for example, Big O of a constant is faster than Big O of log n, which is faster than linear, which is faster than quadratic, and so forth. It is a measure of asymptotic growth rate. So for example, Big O of 3n squared plus 2n plus log of n is Big O of n squared, since we ignore multiplications by constants and n squared is the largest term. With bisection, we can closely compare it to binary search, which takes log base 2 of n iterations, where n is the number of terms in your sorted array or a fully balanced binary search tree, giving us a Big O of log n. Bisection is something similar. It takes log base 2 of b minus a over epsilon iterations, where b minus a is the interval size, or b minus a over epsilon is the number of terms. This means that bisection has a Big O of log of b minus a over epsilon. What about Newton's method? Newton's method takes log base 2 of log of 1 over epsilon iterations when you're close, which you can rewrite as log base 2 of d, where d is the number of digits of accuracy. In Big O, you would say this is log of d, simply because log in Big O is always assumed to be base 2. Halley's method does something similar. It takes log base 3 of d iterations when you're close, giving us log of d. Now you might be wondering what happened to the base 3. That's because a change of bases logs is the same as multiplying by a constant, so that gets ignored. This means that Newton's method and Halley's method have the same Big O. For something like Dekker's method, which combines bisection and secant method, it has the same Big O as bisection, even though it runs as fast as secant method. This makes Big O less useful for comparing these kinds of algorithms. We've covered a lot in this video, and I'd like to leave you with some key points. You can use 3 errors to compute alpha, and then afterwards compute m. Keep in mind that your first few iterations are about getting close, and that function calls impact your speed. Also, higher alphas don't always save you time, as shown in the earlier example. Keep in mind you won't get your full alpha if you're too far away from your roots. Other things that could keep you from getting that full speed are things like condition of the polynomial, and if there's multiplicity involved. Those are topics for another video. Also, that Big O is less useful for comparing these kinds of algorithms, and now you know why. I have lots of example code for all of these root finding methods on GitHub. As always, thank you for watching. I'll leave an end card to my subscriber milestone video showing how you can help support me on GitHub. If you have other questions about order convergence, please let me know in the comments below. Thank you.